Today we're going to start talking about the Shapley value. If we have a game in coalitional form, where n here is the number of players, or the set of players, I should say, and v is the characteristic function, it is desirable, as we've already been trying to work out here, to come up with a payoff vector which is fair in some sense. When we talked about imputations and the core, the idea was that these were supposed to be fair, primarily in the sense that they'd be stable. Any payoff vector that's in the core has to be an imputation, but it also has to be stable under all possible coalitions. In other words, there's no coalition that gets paid less than that coalition could get entirely by itself. However, there are several problems with this concept of the core. One possibility, and we saw this in the last video lecture, is that you have a game in coalitional form and there's a pretty large set of things that are in the core. There are lots of payoff vectors one could have that constitute the core. Well, that's great, except how do you know which one to take? Some are better for player 1, some might be better for player 2, etc. That brings up just a lot more problems. And of course, a bigger problem is that there are many games where there is no core. And what does that mean? That means that no matter what payoff vector you pick, there'll be some coalition that is unhappy. And not just unhappy, but unhappy in the sense that they have an incentive not to agree to that and just play the game by themselves. Here's a very, very simple example of that. We have a 3-person game where the value of each individual is exactly 1. Any individual playing by herself can get a payout of 1. Each pair, 2 players playing together, can guarantee a payment of 4 for that pair. But if all 3 work together, they can get a total of 5. Now, what can we say about any payoff vector? Assume you have a payoff vector x1, x2, x3. For it to be an imputation, each one has to be at least 1. x1, x2, and x3 each have to be at least 1 so that this payoff vector will be individually rational, so that any individual gets at least what that individual could get by herself. But we also need each pair to sum to at least 4. In other words, we need x1 plus x2 would be at least 4, x2 plus x3 is at least 4, and x1 plus x3 is at least 4. In order for this payoff vector to be stable under all 3 of these coalitions, these 3 pairs, 1, 2, 2, 3, and 1, 3. And of course, we need the sum of all of them, x1 plus x2 plus x3, to be exactly equal to 5, the value of the grand coalition of all 3 players working together. What happens, is this possible to have a payoff vector which meets all of these conditions? Well, I claim no, this is impossible. Why? If you just add up the left sides here, you'll get 2x1 plus 2x2 plus 2x3 have to be greater than or equal to the right sides, which is 12. In other words, x1 plus x2 plus x3 has to be at least 6, which immediately contradicts the fact that the 3 players together can only achieve a payout of 5. So what does that tell us? It tells us anytime you have a payout vector with the sum of the entries equal to 5, and we can't get more than that, then one of these 3 has to be violated. In other words, there will be a coalition, there'll be one of these pairs, at least, which is unhappy, and the payoff vector is thus unstable through that coalition. And yet still, if the players are going to play this game, some decision has to be made as to a payout. Is there any way, some canonical way, to produce a fair payoff vector? Well, of course, there's no one canonical way, but we can look at the attempt at this by a mathematician named Shapley, called the Shapley function, and this will give us a way to assign a payout that's fair in exactly the following sense that we'll talk about in a few seconds here. So we start with the idea that the Shapley function or value function phi assigns to the characteristic function v of a game an n-tuple, phi1 of v, phi2 of v, up to phi n of v. And this n-tuple will represent the payout, the player 1, player 2, through player n. So you give me a characteristic function v, phi of v tells you what the payout should be to each player. Now, Shapley's axioms are the following, and the idea is that they all should make sense, so we should want a payout function, or a payout n-tuple, that meets these conditions. What are these axioms? The first is efficiency, which is like saying that the payoff vector has to be group rational. The sum of all the entries, the sum of the entries in this n-tuple, has to be the value of the grand coalition. So for the payout vector we want, the sum is the highest possible sum, the value of that grand coalition. Symmetry. Symmetry says if you have two players which have the following property, when you add them to any coalition that doesn't already include them, you add them to that coalition, you get the same thing whether you add player I or player J. In other words, we start with the empty coalition. We already know that V of the empty set is 0. If we add I to it or add J to it, that tells us that, or we get the value of I and the value of J. Now, if you have two players I and J such their values are equal, but not just that V of the singleton set I equals V of the single set J, we need that to be true, but we need their contribution added to any other set that doesn't already include them, any other coalition, I should say, that doesn't include them. If the values are the same, then we think of those two people as being in a purely symmetric position relative to this game, and of course, the axiom says their payouts in the end should thus be equal. They provide the same value no matter what coalition you add them to. They should get the same amount in the end. Here's a similar condition, but in an extreme sort of sense. If you have a player I, where adding I to a coalition S doesn't change the characteristic function, in other words, player I doesn't add any value if you add him to any coalition that doesn't already include him, then we'll say that that player deserves 0. And that certainly makes sense. There's no benefit from adding that player to your coalition. And finally, we have a technical axiom, which seems like it makes sense, but that's where everything works as far as the mathematics is concerned. It's called additivity. If we imagine applying this Shapley function to different characteristic functions, then the Shapley function for the sum of the characteristic functions u plus v should just be the sum of the Shapley functions at each individual characteristic function. And we should note that if u and v are characteristic functions for some game, say with n players, then when you add them together, you'll get another characteristic function. The only thing to check about that is that superadditivity still works, and it's easy to see that it will. So if you have a way of assigning to characteristic function u a payout, and a way of assigning to characteristic function v a payout, and here you get those payouts, then if you just look at the game whose characteristic function is u plus v, you should just get a payout function, which is the sum of the two you chose individually for u and v. The more you think about it, the more you see that should make sense. But as I said, that's where really all the hard work comes in figuring out how the Shapley function behaves. Now, the first question when you see these axioms, you think, okay, of course the payout function should satisfy all these. Is there even always a way to do that? Just like we saw earlier, of course, a fair payout function should be stable under any coalition, but sometimes that's impossible. We just saw an example of that. Maybe it's impossible to have a Shapley function that works like this, that satisfies all of these axioms. Well, it turns out it is possible to have one, and it's always unique. And the proof of this is not just an abstract proof, but it's a constructive proof, at least mostly a constructive proof. Here, we'll see most of it now, and then we'll finish it up later. So we have a constructive way of finding the unique Shapley function for a particular characteristic function V for a game in coalitional form. So that's what I just said here. Given a game in coalitional form, if you tell me n and v, there's a unique Shapley function, phi of v, a unique payoff vector that satisfies all of those axioms. In order to figure out what it is, and even to show it exists, let's start with the idea of a very simple characteristic function. So a characteristic function for a game, as we've seen, can be all sorts of different things, all very complicated. But here's a very simple type of characteristic function. We'll call it a special characteristic function, which depends on a coalition S. The characteristic function W sub S will just tell you will just give you a value of 1. I'm sorry, let me start that again. A characteristic function has to tell you the value for any coalition, say T. And we'll say W sub S of that coalition T gives you 1 if S is a subset of T and 0 otherwise. This is why we think of this as a special characteristic function. You have one of these characteristic functions associated for each S contained in N. Is it easy to determine the Shapley function for one of these special characteristic functions? Well, these are so simple that the axioms tell us immediately what phi of W sub S must be. Why is that? Well, we want to know, remember, phi of W sub S has to give you this payout vector. Phi 1 of W sub S, phi 2 of W sub S, through phi sub n of W sub S. And we ask, what is phi sub I at W sub S? We want to know the assigned value here for the ith player. How much does the ith player receive from a game whose characteristic function is W sub S? Well, the claim is if I is not an S, then the value should be 0. Why? Because if I is not a member of S, then player I acts like a dummy player in this game, doesn't add any value to W sub S. Why is that? Well, look the way W sub S is defined. It gives you 1 if S is a subset of T, 0 otherwise. If player I is not in S, then adding player I to a coalition T doesn't change whether S is a subset of T or not a subset of T. It'll be the same whether or not you added I. I wasn't in T to begin with. So we know immediately that phi sub I of S is 0. Phi sub I of W sub S, is equal to 0 whenever I is not in S. So many of these automatically have to get a 0 whenever I is not in this subset S for our special characteristic function. And what happens when you add all of these together? Take the sum of every entry here. Well, the claim is that has to be 1, because 1 is the total value, in this case W sub S of N. That will be 1. The grand coalition gets 1 because, of course, S is a subset of the grand coalition. So just by efficiency, this is the idea of making the payoff group rational, you need the total sum of the entries to be exactly 1. Well, if the total is 1 and you have zeros for every player I which is not in S, what can you say about the value for the players that are in S? Well, by the symmetry axiom, the values for all the players that are in S must be identical to each other. Why? Because the effect of adding a player to a coalition is exactly the same for each individual player that is in S. How is that? Well, if you take a coalition T and add a player I that's in S, maybe you'll change the value W sub S of T from 0 to 1. Maybe you won't. But if 2 players are both in S, then they'll have this same effect of either changing the value from 0 to 1 or not changing the value from 0 to 1. So that tells us that the Shapley values for players I and J, if they're both in S, should be identical. Now, if those are identical and they sum to 1, remember zeros for the ones that aren't in S, then that tells us that if you look at the number of players in S, you add those Shapley values together to get exactly 1. Each one has to be 1 over that number of players that are in S. So this tells us a very simple thing, that phi sub I of W sub S is 1 over the size of S for each I in S and 0 otherwise. And it's a triviality to change from one of these special characteristic functions to, say, a scalar multiple of that, a constant times one of those characteristic functions, say 2W sub S, and that just means you'll have to double the value of each entry. Or in this case, if you multiply W sub S by C, you'll have to multiply the outputs by C in each case. So we can say that the Shapley value, phi sub I of C W sub S, is just C over the size of S for members of S and 0 otherwise. Now, why are we looking at these special characteristic functions? Well, we do this a lot in mathematics, especially in areas like linear algebra, where we can take an arbitrary thing and break it down into a linear combination of these special things, say things from a basis. Well, in some sense, we can think of these special characteristic functions as a basis for general characteristic functions, in that we can write any characteristic function for a game in coalitional form as a linear combination, just a sum of constants times these special characteristic functions. So now, how are we going to do that? Why is it true that given a characteristic function v, we can write it as a sum of, and here this sum goes over all subsets of our set of players. For each subset of n, we're going to look at the characteristic function, special characteristic function for that subset, times the appropriate constant. C sub s here will be a constant that depends on which subset we're choosing. I claim you can write that because I'll show you a simple way of computing what the C sub s's are that will make this work. So again, even the proof that we can do this is entirely constructive. So this is not really that tricky a thing, but does take a little bit of work. We'll define these constants. So say t is a subset of n. We want to know what is c sub t. This is that coefficient in this decomposition of a characteristic function v into this linear combination of special characteristic functions. What is that constant? Well, we'll define it inductively on the set t. We just start with the trivial thing. If our subset t is the empty set, the constant will be 0. We're not going to want to talk about using a characteristic function of the empty set, so we want that one avoided right away. We can then define the characteristic function, the constant c for a subset of n, a coalition t. We can define it in this one simple way. Take the value of t using your original game's characteristic function v. So take v of t and subtract the sum of all of these constants that we've already computed for all subsets of t. And here I mean proper subsets of t. S is not equal to t. And if we take this value of t and subtract all those earlier constants, by say earlier meaning for all subsets, the proper subsets of t, we'll get what we want to use for c sub t. And in this way, we've recursively defined these constants for any subset of n. You want to know what c of the set 1 and 2 is? You start by taking the value of that set 1 and 2 and subtracting these constants for all the smaller sets. So you need to know those already. C of the set 1 and C of the set 2. And of course C of the empty set, but we can always kind of ignore that because that's just going to be 0. Now, why does this assignment of constant C sub t actually work, give us the correct decomposition? Well, if I take this sum over all subsets of our players n of the constants that we've just chosen times the corresponding special characteristic functions, and I apply that to some subset t, I claim that just gives us the same as the sum for subsets s of t of the constants. That might look a little weird, but why is that? It's because what is the value of w sub s of t? that value will be 0 if S isn't a subset of T, so I can ignore all the cases where S is a subset of N but not a subset of T, focus only on the S's which are a subset of T, and whenever S is a subset of T, this quantity W sub S of T is just equal to 1. So I'll just write this equal to 0 or 1, and if we add up all the ones where this quantity is exactly 1, that means we're summing just over subsets of T of these constants C sub S. And by the way, I've defined this sum. This sum is the same as this sum, only it includes the C sub T, so I can write it as C sub T plus this sum. And if you just look at this equation, move this over to the other side, you'll see C sub T plus this sum is exactly V of T. So what does that tell you? It tells you our characteristic function V is the same as this linear combination of the W sub S's, regardless of what T you're applying it to for any subset T of N. So that means that V, our original characteristic function, is the same characteristic function as this combination of the special characteristic functions. And that's what we wanted to show. Now, what can we do with that? Well, we can then compute the Shapley values. How do we compute Shapley values using that? Well, we can do it in lots of different examples. I'll just show one example here. Let me go back here real quickly. To compute the Shapley value for V, we just take the same combination. Let me write it like this. Phi of V will just be a sum for S contained in N of C sub S times phi of W sub S. We know how to compute these very easily. What was phi of W sub S? Remember, this was just equal to 1 over the size of S when you're looking at this. Let me say this again. The ith component of this, when you're looking at phi sub I of W sub S, is just 1 over the size of S. So we can compute phi of V by computing it component by component for I equals 1, 2, 3 up to N, by applying this to I equals 1, 2, 3 up to N. And for those, the computation of phi of W sub S is very simple, and then we add them together, and we get the full result.